The latest version of DeepSeek AI's large language model, LLM, is DeepSeek-V3, released in late December 2024. While subsequent models like DeepSeek R1 and R10 have garnered significant attention in early 2025 for their reasoning capabilities, the foundational specifications, chip usage, and power details are most comprehensively documented for DeepSeek-V3. Below is a detailed description based on available information, focusing on its specifications, chip usage, power considerations, specialties, and strengths. Note that specifics for R1 and R10 build upon V3's architecture but lack fully disclosed technical details in some areas, so V3 serves as the primary reference point, with R1 insights included where applicable. Specifications. Chip and power. DeepSeek-V3 is a mixture of experts, MOE, model, with a total of 671 billion parameters, of which only 37 billion are activated per token during inference. This selective activation reduces computational overhead significantly. The model was trained using 2048 Nvidia H800 GPUs over 2 months, equating to approximately 2.8 million GPU hours. The reported training cost was around $5.57 million USD, a stark contrast to models like Meta's Llama 3, 30.8 million GPU hours on 16,384 H100 GPUs, or OpenAI's GPT-4, estimated over $100 million. The Nvidia H800 is a downgraded version of the H100, designed to comply with US export restrictions to China, featuring reduced performance but still substantial computational power. Posts on X suggest input throughput of 73.7K tokens per second, TPS, and output of 14.8K TPS on H800s, though these figures are unverified claims and should be treated as anecdotal. Power consumption specifics for the H800 cluster are not explicitly detailed in public sources, but the efficiency of DeepSeek-V3's training suggests a lower energy footprint compared to competitors. For context, a single Nvidia H800 GPU has a thermal design power, TDP, of around 300 or 400 watts, depending on configuration, meaning the 2048 GPU cluster likely consumed on the order of 600–800 kWh during peak operation. DeepSeek's optimizations, such as FP8 mixed precision computation and the dual pipe algorithm, further reduce power demands by minimizing idle time and optimizing GPU communication. However, some analyses, e.g. from MIT Technology Review, note that while training is energy efficient, inference might offset these savings due to intensive reasoning techniques and longer outputs, though exact power metrics remain undisclosed. Specialties, mixture of experts, MOE, architecture. DeepSeek-V3 employs an MOE design with specialized and shared experts, activating only 37 billion parameters per token. This reduces memory and compute needs compared to dense models, enhancing efficiency without compromising performance. Multi-head latent attention, MLA. This mechanism compresses key value stores during inference, reducing memory usage to 5 tau and 13% of traditional methods, making it ideal for long context tasks, up to 128,000 tokens. Multi-token prediction, MTP. Unlike traditional models predicting one token at a time, V3 predicts multiple future tokens simultaneously, boosting speed and reasoning capability. FP8 mixed precision computation. By using 8-bit floating point numbers with custom GM routines for accuracy, V3 cuts computational costs and memory usage, supported by tile-wise and block-wide quantization techniques. Reinforcement learning, RL. Focus for R1, built on V3. DeepSeek uses pure RL with rule-based rewards to enhance reasoning, avoiding reliance on external critic models, a shift from supervised fine-tuning norms. Strengths, cost efficiency. Training V3 for under $6 million challenges the narrative that cutting-edge AI requires massive budgets, democratizing access for smaller entities. R1's open-source release amplifies this by offering high performance at no direct cost to users. Performance parity. V3 rivals top-tier models like GPT-4o and Claude 3.5. Sonnet on benchmarks, e.g. math, coding, while R1 matches OpenAI's O1 in reasoning tasks, despite using less powerful hardware. Hardware optimization. DeepSeek's use of H800 GPUs, paired with innovations like the dual-pipe algorithm, overlapping computation and communication, and PTX programming, fine-tuned GPU control, maximizes efficiency on restricted hardware, a necessity driven by US chip bans. Scalability. The MOE design and memory optimizations allow deployment across varied hardware, from enterprise clusters to potentially smaller setups, e.g., M3 Ultramax Studios with 512 GB memory for fine-tuning, as noted on X. Multimodal potential. While primarily text-focused, V3's integration with AMD Instinct GPUs and SGLang hints at future multimodal capabilities, text and visual reasoning, broadening its application scope. Additional notes: DeepSeek's approach reflects a strategic response to US export controls, leveraging stockpiled Nvidia A100s pre-ban and H800s with software ingenuity. Critics question the $557 million figure, suggesting it omits sunk costs, e.g., data centers, staff, with estimates like Semi-Analysis proposing a $1.6 billion total capex. Regardless, the model's efficiency is undeniable, shaking industry assumptions about resource needs. Its open-weight release, not fully open source due to proprietary training data, further amplifies its impact, though privacy concerns have led to bans in some regions. In summary, DeepSeek-V3, and by extension R1, combines a 6x71B parameter MOE architecture, trained on 2048 Nvidia H800 GPUs, with groundbreaking optimizations like MLA, MTP, and FP8 precision. Its specialties lie in efficiency-driven design, while its strengths cost, performance, and adaptability position it as a disruptive force in AI, challenging both technical and economic paradigms.